In the first chapter, we covered the fundamentals. What does A&P even mean? Anatomy and physiology. We talked about the organ systems and some key vocab. And now let's start at the very bottom, the small stuff. So starting at the top, we have an organism. You, me, all the people out there, they're made of organ systems, which have a bunch of different organs all working together for a function. We're going to study those organ systems in isolation, but we know they all work together. The organ systems are made of organs. Organs are made of tissues. Tissues are made of cells. Cells are made of macromolecules, which are made of molecules, which are made of atoms. So in order to understand the organism, we have to understand all the levels that come before that. So we're going to start at the very bottom here, at matter, energy, atoms. And so we're going to talk about what is matter and energy, what matter is composed of, what are molecules, what are compounds, chemical bonds, chemical reactions, biochemistry. So for this first section, I want you to be able to differentiate matter from energy and talk about the four major energy forms and how they're used in the body. So I want you to first think about this question. So how would you define matter, energy, elements, atoms, and isotopes? These are words that are probably familiar to you, but you might not be able to actually put a definition on it. So I want you to pause the video, take out a piece of paper and a pencil or a pen or a Word document on your computer, and try to define these words. Can you figure out exactly what they mean? Okay, I'm assuming you've done that. You've paused it, you're back, you have your definitions. Let's see if you're right. So matter, this is the stuff of the universe. This is anything that occupies space and has mass. We're talking about solids, liquids, and gases. Those are the phases of matter. Hopefully this is ringing a bell. A physical change is when we move through those states, like taking an ice cube and melting it, from solid to liquid. A chemical change is when we alter the chemical structure of what we're working on. And energy allows us to do some of that. So energy is the ability to do work. We're talking about kinetic energy or potential energy, and it has a bunch of different forms like chemical energy, electrical, mechanical, radiant. And energy in our body is often converted. So we start with chemical energy from our food, and we convert it to things like mechanical energy, moving our muscles, electrical energy in our nerves, which send out electrical signals, and we also lose some of that as heat. So hopefully you are now able to define matter and energy. Let's talk a little bit more about some of the other key terms. Let's see if we can define the chemical element and list the four major elements in the body and talk about how atoms and elements are related and the subatomic particles, where they are, what they're made of, what their charge is. And finally, let's see if we can define radioisotopes. So matter is made of elements which cannot be broken down by ordinary means. And there are a bunch of them, but I really only want you to know the major ones in the body. The four most common by mass are oxygen. So oxygen, most percentage of body mass, 65% of your body is made of oxygen. It's in everything, okay? The other big one is carbon. You're going to see this in all of the macromolecules we talk about. Some of the other ones that are important, hydrogen, nitrogen, calcium. Calcium is found in our bones and our teeth. It's required for nerve and muscle contraction. Phosphorus, this will be important when we talk about ATP, which is the energy of the cell. Potassium is also involved with nerve impulses and muscle contraction. Sulfur is a big part of proteins. Sodium and chlorine, these are abundant ions. Magnesium is important, it's also in bones. Iodine is important for your thyroid hormone, and iron is in hemoglobin. Okay, so elements are made of identical atoms. Elements are made of identical atoms, and atoms have subatomic particles, our protons, electrons, and our neutrons. Where are they? Protons and the neutrons are in the nucleus. That's this thing right here. And they have mass, they have weight to them. Protons are positively charged, neutrons are neutral. The things floating around the edges, those are our electrons, which have virtually no mass and a negative charge. Now, I'm going to show you the electrons in what we call the planetary model, which is going to show these little lines which track electron movement like planets around a sun. However, in actuality, electrons are in these clouds, which show probability, these orbitals. I'm not going to get into orbitals. I will save you that headache. I'm going to instead show you them in planetary form, but know that in actuality, they're these fuzzy clouds. Okay, how do we identify an element? We identify an element based on a few different things. So the atomic number is the number of protons. This is unique. So if you see 6 protons, for example, you know you're dealing with carbon. It's identifying. The atomic mass are all of the weighted things. So that's the protons plus the neutrons. However, when you look at a periodic table, you'll see a number with a decimal point. And this is the atomic weight. So it's a weighted average that takes into account the fact that there are carbons. Most of the time, their atomic mass is 12. But we have some carbons that are heavier. Some are carbon 13 or carbon 14. And we'll get back to those in a minute. Okay, here are some common atomic structures: hydrogen, helium, lithium. So we're adding on these orbitals, these rings for our electrons. Isotopes. So I said I would get back to carbon 13 and 14. Here's where they appear. Isotopes are atoms that vary in the number of neutrons. So this is going to alter our atomic weight. What do I mean by that? I mean that carbon, most of the time, it's 12. It's got 6 protons and 6 neutrons. But sometimes it's carbon 13. It's got 7 neutrons or 8 neutrons. Now, if it's stable, it's a stable isotope. That means that it's very happy to be carbon 13 or carbon 14. However, sometimes you can have unstable isotopes, and we call these radioisotopes because they're going to decompose and they're going to lose extra neutrons until they reach that happy point. And that loss, that decomposition, leads to something that we can pick up with machines called radioactivity. So a lot of imaging in medicine is based on radioisotopes. You'll be injected with a radioisotope tracer, for example, that will bind to certain things or show you certain things that you can then detect with imaging. So again, hydrogen isotopes. Most of the time, it's got 1 electron and 1 proton, except sometimes we got an extra neutron or 2 extra neutrons, and these will decay if they're radioactive, if they're unstable. These are the most abundant elements, again, in the body, showing you their atomic number and what that means for their atomic weight and what that means for the electrons in the valence shell. The valence shell is the outer shell, and that's the most important one for electrons. So, can you now define these terms? Can you now define matter, energy, elements, atoms, isotopes?